Hi, my name is Jiaqing Yang and my ZID is z5695115. Hello everyone, today I'll be your host and I'll be exploring Kepler's laws and the results I've discovered in the experiment. Kepler's first law states that planets move in elliptical orbits, not perfect circles, with the Sun located at one of the two foci. This is seen in the animation below. Kepler's second law states that a line joining a planet and the Sun sweeps out equal areas in equal intervals of time. This also means that when a planet is closer to the Sun, it moves faster, and it moves slower when further away from the Sun. Kepler's third law states that the square of the orbital period of a planet is directly proportional to the cube of the semi-major axis. Now that we've uncovered what Kepler's laws are, let's explore the applications in the experiment. Let's take a look at a simulation of the Earth-Moon system. Notice that as the Moon orbits the Earth in a circular path, the Earth appears to wobble a little bit during the orbit. This effect is due to the system's center of mass. The following sections explore how the center of mass influences orbital motion in different systems. The center of mass is the balance point of multiple interacting bodies, where each object's contribution is proportional to its mass. Therefore, the center of mass lies closer to the more massive object. In questions 1, 4, and 7, the Sun is significantly more massive than the planet, so the center of mass lies very close to the Sun's center in all three cases. In the Sun-Earth scenario, the Sun is about 330,000 times more massive than the Earth, so the contribution of the center of mass from the Earth is insignificant. As a result, the center of mass lies very close to the Sun, which is why the Sun appears almost stationary. In contrast, the Earth and Moon are more comparable in mass. As the Earth is about 81 times more massive than the Moon, this mass difference is much smaller than the Sun-planet scenario. Consequently, the center of mass lies outside of the Earth's center, causing both the Moon and the Earth to orbit their common center of mass. The actual distance between the Earth and the Sun in astronomy is 1 astronomical unit, which is about 150 million kilometers. The distance in the simulation accounts for 2 grids, so the distance between each marking is approximately 0.5 AU. Understanding this is important because we'll use the scale for the next part of the experiment. So for instance, we wanted to measure the relationship between orbital distance and orbital period. I chose to change the distance in intervals of 0.25. This is shown in the screenshots on this slide. The results I obtained were quite interesting. As you can see in the table below, incrementing the orbital distances does also increase the orbital period. However, I wanted to analyze this relationship further, so I decided to plot a graph. This allowed me to determine that it did satisfy Kepler's third law. If you graph the original data, the relationship doesn't look linear. It translates to more of like a power law type of curve. However, when you take the square of the orbital period and the cube of the orbital distance, the new graph becomes linear. An increase in orbital distance cubed corresponds to an increase in orbital period squared, revealing a clear proportional relationship. As a result, t must be directly proportional to a to the power of 312. Therefore, the simulation results satisfy Kepler's third law. Now, I have a question for you. Have you ever wondered which planet in our solar system travels the fastest and which planet in our solar system travels the slowest? Well, let's find out. When you apply Newton's law of universal gravitation with the centripetal force for circular motion, the orbital velocity can be expressed as square root of gm on r. Since g and m are both constants, a larger orbital radius results in a smaller orbital velocity. Therefore, a planet closer to the Sun moves faster than a planet that's further away. As shown in the diagram, with Mercury being the closest at 0.39 AU from the Sun and has the highest orbital velocity of 47.9 km per second. Meanwhile, Neptune is the furthest planet from the Sun, being at a distance of 30 AU from the Sun, has the lowest orbital velocity, which is 5.4 km per second. To conclude, I would like to talk about what I've learned in this video. For starters, I learned how to apply Kepler's laws of planetary motion in theory and practically in the experiment. The simulation results allowed me to analyze and deduce a relationship between the orbital period squared and the orbital distance cubed. Newton's law of universal gravitation helped explain the underlying force responsible for this motion. And in general, studying astronomy changed the way I view the universe and our place in it. Thank you guys for watching, and bye bye.